Immense water pressure. The first challenge is hydrostatic pressure. For every 10 meters below sea level, pressure rises by 1 full atmosphere of force, about 14.7 pounds per square inch. At 50 meters down, that's already 5 atmospheres, 73 psi. Multiply that across a tunnel, and you're holding back hundreds of thousands of tons, 24 hours a day. The only geometry that can handle this evenly is the circle. That's why virtually all underwater tunnels are circular, lined with reinforced concrete segments up to 2 meters thick. Steel rebar cages are embedded in every segment, and waterproof gaskets are installed around the perimeter. Each ring is compressed tightly by hydraulic jacks during installation, ensuring a perfectly sealed pressure shell. This geometry isn't optional, it's survival. At these depths, construction crews can't just walk in casually. In pressurized working chambers, like in TBMs, workers are exposed to compressed air environments. They often need decompression procedures after shifts to avoid the bends, just like divers. Some megaprojects even had on-site decompression hospitals. Geotechnical Investigations. Before a single machine starts, engineers map the seabed in detail. Multi-beam sonar scans the ocean floor. Sub-bottom profilers show sediment thickness. Boreholes bring up soil and rock cores for lab testing, measuring strength, permeability, and chemical composition. Piezometers track groundwater pressure. This data decides everything: the tunnel's depth, its alignment, and which construction method will work without failure. Miss a fault zone or weak soil pocket, and the tunnel's doomed before excavation begins. Tunnel boring machines, TBMs. For deep alignments and when geology's strong enough, TBMs are the weapon of choice. These are 4,000-ton mechanical monsters, a steel cylinder the length of 4 jetliners, with a rotating cutter head as wide as a 12-story building. Cutter head rotates, equipped with dozens of tungsten carbide discs. Each disc exerts hundreds of tons of pressure to crush rock. At the face, tungsten carbide discs crush rock, while slurry systems or conveyors carry spoil away. Behind, hydraulic jacks push forward, while erectors place pre-cast lining segments in perfect rings. The TBM moves forward by bracing against its own freshly built tunnel. Sensors measure face pressure, torque, and advance rate constantly, adjusting in real time to avoid collapse or surface settlement. Segmental linings. The tunnel's armor is built 1 ring at a time. Each ring is formed of 6 to 8 curved concrete segments. These are cast in specialized yards, steam-cured and tested for strength and water absorption. Steel fibers prevent cracking. Gaskets are pre-fitted into grooves. When the erector locks a ring into place, the gaskets compress, creating a watertight joint that gets tighter under pressure. The tolerances are millimeters. A poorly cast segment or a misaligned gasket could mean a leak that grows into a disaster. Immersed tube method. In shallow water or soft seabeds, immersed tube tunneling is used. Think of it as building an underwater Lego set, piece by piece. Engineers build giant hollow tunnel sections in dry docks, sometimes 180 meters long and weighing up to 55,000 tons. They're made from reinforced concrete, steel frames, or hybrid designs. Bulkheads are fitted to both ends, making the section buoyant and watertight. Tugboats tow sections like floating submarines to the installation site. Dredgers have already cut a trench in the seabed and laid a gravel foundation. Then ballast tanks flood slowly, sinking the section into position. Divers and ROVs guide it with centimeter precision with an alignment tolerance of just plus or minus 20 millimeters over hundreds of meters. Joints between sections use double gaskets. GINA, flat rubber sealing gasket, seals for compression. It's made of ethylene propylene diene monomer synthetic rubber, or EPDM, designed for water tightness and durability under pressure. Then Omega seals for flexibility, typically made of thermoplastic elastomers or steel rubber composites, shaped like the Greek letter omega, to lock into grooves and ensure watertight connections. Once joined, the trench is backfilled with sand and rock, locking the tunnel in place forever. Ground stabilization. Not all seabeds are solid. Sometimes they're clay, silt, or sand that behaves like liquid under pressure. Here, engineers strengthen the ground before tunneling. Ground freezing is one method. Pipes circulate brine chilled to minus 30 degrees Celsius, turning soil into frozen rock. Some projects use liquid nitrogen for faster results. The frozen ground acts as a temporary watertight wall, letting excavation continue safely. Jet grouting is another method. High-pressure jets inject cement slurry, forming underground hardened columns. In older projects, compressed air was used, pressurizing chambers to hold water out. Workers dig in pressurized chambers. The extra air pressure counteracts water ingress, but this method is risky. Too much pressure can cause decompression illness, and historically, it killed many workers. Today, it's limited due to health risks, but the principle remains the same. Stabilize, then dig. Seals and waterproofing. Waterproofing is the difference between success and catastrophe. Every joint has multiple defense layers, rubber gaskets, steel shear keys, injected grout, all designed to resist inflow. In immersed tubes, omega seals span the joint, allowing for slight movements without losing water tightness. Continuous monitoring is essential. Sensors track humidity, strain, and seepage. A leak the size of a pinhole can, under pressure, erode concrete into a torrent. That's why redundant pumps are installed in every section, always on standby. Ventilation. In daily use, the challenge is vehicle exhaust. Road tunnels generate carbon monoxide, nitrogen oxides, and fine particulates. For rail tunnels, braking and traction create heat and ozone. Engineers design airflow to keep contaminants below safe thresholds, often 30 to 50 parts per million for carbon monoxide and even stricter for nitrogen oxides. Here are two used ventilation methods. Jet fans. Most underwater road tunnels use longitudinal jet fans mounted at the crown. Each fan accelerates a jet of air, creating thrust that pulls the entire airflow along the tunnel bore. A 3-kilometer underwater tunnel may require dozens of fans, each capable of 250 to 300 newtons of thrust. Transverse ventilation. In longer or multi-lane tunnels, ducts embedded in the lining carry fresh air in and foul air out through dampers spaced every 50 to 100 meters. These ducts run above or below the roadway, hidden from drivers but essential to air quality. Fire safety. In a fire, the rules change instantly. A truck fire in an underwater tunnel can release 30 to 50 megawatts of heat, raising temperatures to over 1,000 degrees Celsius within minutes. The priority is smoke, not flames. Smoke kills faster than heat. Engineers install smoke ducts with high-capacity extraction fans, capable of pulling smoke at rates of 200 to 400 cubic meters per second. These ducts can be activated in zones, isolating the fire area and drawing smoke away from evacuation routes. Operators must carefully manage airflow to avoid feeding the fire with oxygen. Fans can be reversed to push smoke in one direction, always away from evacuees. Computational fluid dynamics models guide these scenarios, simulating different fire loads and vehicle positions. Tunnel linings are protected with fire-resistant concrete or intumescent coatings that can withstand 1,350 degrees Celsius for at least 2 hours. Ventilation fans themselves are fire-rated, designed to keep spinning in smoke and heat long enough for evacuation. Hyperbaric Interventions. When TBMs need cutterhead maintenance in pressurized ground, workers must enter the excavation chamber. Pressures reach 3 to 4 bars, equivalent to diving 30 meters underwater. Crews enter through manlocks, work for short shifts in compressed air, and then decompress for hours to avoid the bends. Tasks are done in darkness, under noise, in extreme humidity. It's one of the most dangerous jobs in tunneling, requiring medical supervision, decompression chambers, and specialized training. Spoil management. Excavating a tunnel produces millions of cubic meters of material. Slurry TBMs pump it out mixed with bentonite. Surface plants separate soil using shakers, cyclones, and centrifuges, recycling the bentonite for reuse. In EPB machines, conditioned muck is carried on conveyors and stockpiled. Disposal sites must be ready, or in some projects, spoils reused for land reclamation or bricks. Waste logistics run in parallel with excavation. If spoil isn't cleared, the TBM stops. Monitoring and control. Every step is tracked by instruments. Settlement markers and total stations measure surface movement. Inclinometers detect ground deformation. Piezometers track groundwater pressure. Inside the tunnel, strain gauges and convergence meters measure lining performance. All data flows into control rooms in real time. If settlements exceed limits, crews adjust TBM pressure, change advance speed, or modify grout mixes immediately. Underwater tunnels cannot afford surprises. Electrical backbone. Medium voltage feeders run through fire-rated ducts along the tunnel. These connect to transformers and switchgear housed in underground substations. Emergency loads, pumps, fans, lighting, communication, are supplied by uninterruptible power systems, or UPS, and backup diesel generators. Cables are fire-resistant, laid in separate fire compartments to avoid single points of failure. Control and SCADA. Every mechanical and electrical system feeds into SCADA, supervisory control and data acquisition. Operators in centralized control rooms see live data on airflow rates, fan thrust, pump capacity, power loads, and temperatures. Algorithms automatically switch fans, open dampers, or start backup pumps if anomalies appear. CCTV integrates with automatic incident detection. AI systems flag smoke, stalled vehicles, or pedestrian movement instantly. Drainage and pumping. Even a perfectly sealed tunnel allows microseepage. In deep tunnels, inflows can be thousands of liters per minute. Drainage pipes in the invert collect water, directing it to sumps. Each sump has multiple pumps and N+1 redundancy, meaning at least one spare capacity pump. High-lift pumps can discharge water tens of meters back to surface reservoirs, even during floods. Communication networks. Safety depends on instant communication. Radiating coaxial cables, also called leaky feeders, act as continuous antennas, enabling radio and cellular signals underground. Emergency phones and fire alarm boxes line the tunnel every 150 meters. PA/VA, public address, voice alarm systems, can broadcast evacuation orders within seconds. Lighting and guidance. LED lighting systems are zoned, dimmable for energy efficiency, but capable of instantly switching to high output during emergencies. Photoluminescent strips line curbs and walls, glowing even during blackouts, guiding evacuees to exits. Signs are often bilingual, illuminated, and backed by independent power circuits. Testing and commissioning. Every system is tested in integration. Pumps and fans running under simulated blackout. SCADA responding to injected faults. Communication tested with fire crews and breathing apparatus. Integrated system testing runs through real disaster scenarios, verifying that power, ventilation, communication, and control work as one machine. Seismic and settlement design. Tunnels crossing faults or soft-stiff transitions need flexibility. Immersed tubes use expansion joints and omega seals to absorb ground movement. In bored tunnels, joints are designed to handle differential settlement. Designers simulate earthquakes, storm surges, and even ship anchor strikes above the tunnel. Buoyancy during dewatering, pressure reversals, and scour are all considered. The tunnel's built not just for today's conditions, but for a century of environmental forces. Environmental management. Marine ecosystems are considered. Dredging creates turbidity, so engineers use silt curtains and limit work to save seasons. Pile driving is muffled with bubble curtains to protect marine mammals. Bentonite slurries recycled to avoid ocean discharge. Spoils tested for contamination before disposal. Many projects include habitat offsets, like creating wetlands or artificial reefs. Colossal costs. Underwater tunnels are among the costliest infrastructure on Earth. A single kilometer can cost $500 million to over $1 billion. Why? TBMs custom-built for each project cost over $100 million apiece. Segment casting yards require factories turning out rings every hour. Marine fleets, dredgers, barges, tugboats burn millions per day. Shafts, cofferdams, and portals are entire projects on their own. Safety systems, pumps, and ventilation can equal the cost of excavation. And then comes maintenance. Pumps and seals run constantly. Over a century, total life cycle costs can double the initial bill. These projects are measured not in millions, but in tens of billions. Operations and lifespan. Once complete, the tunnel becomes a living system. Pumps handle seepage. Fans exchange air. SCADA systems monitor every sensor. Crews inspect gaskets, repair cracks, replace fire systems, and renew tracks or road decks. Cathodic protection keeps steel from corroding. Digital twins and sensor data guide predictive maintenance. The design life is often 100 years, but only if the tunnel's treated as a patient under constant medical care.